very warm welcome to all of you who are watching this video. Due to the coronavirus pandemic, our life is under complete lockdown. Quarantine, homestay, isolation are the unpleasant realities of our lives at the moment. We all know that things started sinking in when the board examinations were cancelled, IPL was postponed, and we were told to stay at home in isolation and to work from home. I have never seen in my life such collective anxiety and concern. Moreover, our WhatsApp groups are full of strange theories on the pandemic. No one bats an eyelid before sharing the posts, even they know can't be true. Dear students, at the moment, we all have enough of free time, even though we are engaged in one assignment or the other. But what I want to say that having all that free time was indeed very exciting initially, but now it is imperative to use this time wisely. Time is one thing that once spent can never be earned back. Any kind of knowledge will only benefit, so make good use of this time and learn something. It would be very much beneficial for the students to acclimatize with the topics that are going to be covered. So getting a start ahead on your studies will help you in keeping up with your curriculum. So self-study is the norm now more than ever. But studying by yourself is also not an easy task, as we all need assistance in one form or the other. Thanks to technology today, a lot can be learned from within the comforts of our homes. So let's use this technology to study one of the most simple but important topics of mathematics, number system. Also, one more thing I would like to tell, that this video lecture cannot be a replacement for regular class, but only supplement it. Once again, welcome all of you. The great mathematician of Egypt, Pythagoras, quoted, "Numbers rule the universe." So let's start with the topic number system. And though the topic is very simple, but I must tell you that there is a lot of confusion or doubts in the minds of the students regarding this chapter, and this continues till the higher level. You need to learn this topic at the school level only, because after that this topic will not be taught anymore. For example, if you are taught addition in the lower class and you have not learned addition properly, so it is definitely going to create problem for you. So this topic, which is now taught in class 9, will not be taught in the higher classes anymore. So watch this video lecture carefully and with motivation. I hope it will help you to clear all the confusions, if any. We have already learnt about the various types of numbers and the representation on the number lines in the lower classes. Let's first start with what is a number line or a real number line. In mathematics, the real line or real number line is the line whose points are the real numbers. So you can see this is the number line where there are infinitely many points, and each of the points are assigned a number, and these numbers are all real numbers. Now what are real numbers? In due course of time we will be coming to know about the real numbers. Now this is a one-dimensional graph. Just like assigning addresses to the houses on a street, we assign addresses to the points on the line. We assign 0 to the center of the line and we call it the origin, right? Now we assign the directions with signs: positive to the right of this origin, that is towards east, and negative to the left of the origin, that is towards west, right? So this line with each position addressed by a number is called a number line. Is it clear? Okay. Now we move on to the next topic. Just imagine you start from 0 and go on walking along this number line in the positive direction. So as far as your eyes can see, there are only numbers, numbers and numbers. Now suppose while walking along the number line, you start collecting some of the numbers in a bag. You begin with picking up only numbers like 1, 2, 3 and so on, and this list goes on forever. That is, there are infinitely many such numbers called natural numbers, and we denote this collection by the symbol capital N. Now the question is, how will you define a natural number? Now before we define what is a natural number, let me tell you that there are two categories of numbers on this number line. What are those? Fractional numbers, 1 by 2, 2 by 3, 6 by 7, and so on. And non-fractional numbers like 1, 2, 3, 4, and so on. So, natural numbers are the set of non-fractional numbers from 1 to infinity. So, we can define natural numbers as the set of non-fractional numbers from 1 to infinity. Am I clear? Okay. We can also refer to the definition, we can also tell the definition like the set of all counting numbers, because we start counting from 1. Hence, this definition is sometimes found somewhere like the set of all counting numbers are also called natural numbers. Now, there are two facts about natural numbers. First one, the sum of any two natural numbers is always a natural number. For example, if we write 3 plus 2, that is equals to 5. If we write 4 plus 6, we get 10. So what we see, that adding any two natural numbers, we are getting the result as a natural number, right? And number 2. So first one is the sum of any two natural numbers is always a natural number. Now second is the difference of any two natural numbers. The difference of any two natural numbers may be a natural number or may not be a natural number. For example, if we do 3 minus 2, we get 1. This is a natural number. But if we operate like this, 2 minus 3, then it comes to minus 1, which is not a natural number. So these two facts sometimes are asked in the form of objective type questions. So we just see that the facts about these natural numbers. First one is the sum of any two natural numbers is always a natural number, and the difference of any two natural numbers may be a natural number or may not be a natural number. Okay. Now turn and walk all the way back. Pick up 0 and put it inside the bag. Right? You now have the collection of whole numbers, which is denoted by the symbol capital W. So what we see here is that the whole numbers are the collection of 0 and all the natural numbers. So we can say all natural numbers are whole numbers, but all whole numbers are not natural numbers. So here also the same two facts applies about the whole numbers. That is, number 1, sum of any two whole numbers is always a whole number, and number 2, the difference of any two whole numbers may be a whole number or may not be a whole number. Okay? Now, so what we know about the whole numbers is that whole numbers are the collection of 0 and the natural numbers. So we can say that natural numbers are the subset of whole numbers. Okay? Now, stretching in front of you are many negative integers or numbers. Put all these negative numbers into your bag. What is your new collection? Yes, it is the collection of all integers, and it is denoted by the symbol capital Z. Why Z? Z stands for the German word Zahlen. Z A-H-L-E-N, Zalin, which means to count. Okay, now how will we define integers? All natural numbers, negatives of natural numbers and 0 together form the set of integers. So all natural numbers, negatives of natural numbers and 0 together form the set of integers. So you can write it like this. So this is the set, which is the set of all integers. You can see clearly 1 till infinity are all positive integers, positive natural numbers, that is the natural numbers, negatives of natural numbers and 0. So combination of all this gives you the set of integers, which is denoted by the letter capital Z. Now if we write Z minus and if we write Z plus, so Z minus represents the set of all negative integers. The set of all negative integers is represented by Z minus, and the set of all positive integers is denoted by this particular 1 to infinity. This is the set which is representing all the positive integers. Now one question arises. If you look at these two sets, we find we have not included 0 in any of the two sets. Whether it is a set of all negative integers or whether it is a set of all positive integers, 0 is not included in either of the two sets. So what is 0? A positive integer or a negative integer? So there is always a confusion regarding this amongst the students. It's very simple. We'll talk about non-negative integers. 0, 1, 2, 3 till infinity. So this is the set of all non-negative integers, which includes 0. So when you talk about non-negative integers, we include 0 in this set, right? Now when you talk about non-positive integers, then we include 0 in that set as well. So if it is non-positive integers, so this is the set of non-positive integers. So 0 can be referred to as both a non-negative integer and a non-positive integer. Okay, it's clear now? Now, are there still any more numbers left on the line? Yes, there are. There are numbers like 1 by 2, 4 by 5, minus 12 by 13 are present on the number line. And if you put all such numbers into your bag, it will now be the collection of rational numbers. The collection of rational numbers is denoted by capital Q. Rational comes from the word ratio. Rational comes from the word ratio, and Q comes from the word quotient. Quotient, quotient. which is an Italian word which means quotient of two numbers, which means quotient of two numbers. Now before we define a rational number, let's discuss a little about fractions. Okay, now what is a fraction? What is a fraction? A fraction is a numerical quantity which is written in the form of a by b, where a and b belongs to natural numbers and a and b are non-negatives. So it actually represents a part of something. So you can write fractions as a by b, where a and b belongs to n. Okay, and a and b are non-negatives. This actually represents a part of something. Okay, now we will define rational numbers. A number r is called a rational number if it can be written in the form p by q, that is, it can be written as a ratio of two integers, that is simple fraction, where p and q are integers and q not equals to 0. Also, one more condition which is very important, that p and q are co-primes. That means p and q has no common factors other than 1. So we see that it can written in the form of p by q, where p and q belongs to z and q not equals to 0. Okay, so this is the form of the rational numbers, which is written in the form of p by q, where p and q belongs to the set of integers and q not equals to 0. Right. Now, notice that all the numbers in the bag, one thing you notice, that all the numbers that are put inside the bag, these are the natural numbers, 0, negatives or natural numbers, and all the fractional numbers that we have just put inside it. So notice that all the numbers in the bag can be written in the form of p by q, where p and q are integers and q not equals to 0. For example, 5 can be written as 5 by 1. 5 can be written as 5 by 1, where p equals to 5, q equals to 1, means that is q not equals to 0, p and q are both integers, q not equals to 0, and they are co-primes. P and q are co-primes. Co-primes means, as we have just discussed, p and q do not have any common factors other than 1. So next is 1.5. This is also a rational number because it can be written as the ratio 3 by 2. Then we can write 0.333, where 3 is repeating. We can write 0.333, where 3 repeating. This is also a rational number because it can be written in the form of p by q, that is, it is the ratio of 1 by 3. So therefore, the rational numbers also include the natural numbers, whole numbers, and the integers. Okay, so we find one more thing. So this bag now is the bag of real numbers, which consists of natural numbers, whole numbers, integers, and all the numbers which are of the form p by q. So this is the correction, which is this bag is now a bag of real numbers. Okay, it's clear? So what you find, that this bag is now a collection of rational numbers. Okay, I think I told you real numbers. No, it's not real numbers. It is the set of or the collection of rational numbers. So rational numbers includes natural numbers, whole numbers, as well as the integers. Now I ask you one question. The question is 0 a rational number or an irrational number? Question is 0 a rational or an irrational number? So it's very simple. You just need to stick to the rules which defines a rational number. Okay. Now what are the conditions of the rules? So it defines a number, which is whether the number is rational or not. First of all, the conditions for a number to be a rational, to be declared as a rational number, is number one, it can be written in the form of P by Q. Secondly, P and Q are integers. Third, Q not equals to 0. And fourth, P and Q are co-primes. That is, P and Q do not have any common factors other than 1. Okay, so now let's see what about 0. So see, we can write 0 as it can be 0 by 1, or it can be 0 by 2, or it can be 0 by 3. Anything we can write. Okay, now it is in the form of P by Q. If we take 0 by 1, it is in the form of P by Q, where P is 0, here P is 0, Q equals to 1. As I told you, the first condition, it can be written in the form of P by Q. So it is written in the form of P by Q, where P is 0, Q is 1. So both are integers. Third, QB is 1, which indicates that Q is not equals to 0. And fourth, P0, Q equals to 1 indicates that they are co-primes. So 0 is a rational number. So to define a number, whether to be rational, the 4 conditions you have to see to, that is, it can be written in the form of P by Q. Secondly, P and Q are integers, Q not equals to 0, and P and Q are co-primes. Now I will give you true false type questions. You just need to answer it. I think whatever you have discussed, you will be easily able to answer the answers. You will be able to answer the questions here. Now I just write the questions on the board. Okay. Right. True or false? Number 1, every whole number is a natural number. Every whole number is a natural number. Second one, every integer is a rational number. Third, every rational number is an integer. Every rational number is an integer. Then number 4, every natural number is a whole number. Number 5, every integer is a whole number. And number 6, every rational number is a whole number. So these are the 6 questions based true false type questions which we have already discussed till now. First of all, every whole number is a natural number. So I think I will leave this on you to answer this question. Okay, I will just write the answers. You need to check it whether they are correct or not. The first one is every whole number is a natural number. This is false. Second one, every integer is a rational number. So I think this is true. Third one, every rational number is an integer. So I think I should write false. Fourth one, every natural number is a whole number. We have discussed this right at the beginning. So this has to be true. Every integer is a whole number. So it is false. And finally, every rational number is a whole number, has to be false. And I think it is clear, very much clear, if you listen to the discussion. So these are the answers. If you are still confused, so refer to the lecture again and see that your concept becomes clear. Okay. See, math classes are always very measurable and happening. So let's move ahead and make it happen. Now so far, all the numbers that you have come across are of the form P by Q, where P and Q are integers and Q not equals to 0. So are there any numbers other than these which are not of this form, that is P by Q? Yes, there are such numbers which are not of this form P by Q, and those numbers are called irrational numbers. So even if we write these numbers in the form of P by Q, the rules cannot be followed as is followed in the case of rational numbers. Examples of irrational numbers are like this: root over 2, root over 3, root 5, pi, 0 0.10, 110, 1110, this. So these are the examples of irrational numbers. Now, how will you define an irrational number? So a number S is called irrational if it cannot be written in the form of P by Q, where P and Q are integers and Q not equals to 0. Means it's just the opposite of rational numbers, where you can write the numbers in the form of P by Q, where P and Q are integers and Q not equals to 0. Okay. Now supposing root 2 is irrational. Now how to prove or how to check whether this number is rational or irrational? So let us check whether root 2 is rational or irrational. It will be clear to us by the contradiction method. So we will adopt the contradiction method to prove whether root 2 is an irrational number or not. So to prove this contradiction method means we will be using or assuming something. Contradiction means we will assume something and we will prove it wrong. Okay. So by the method of contradiction, we will prove that root 2 is an irrational number. Okay. So as I told you, method of contradiction or contradiction method means we will assume something and we'll prove it wrong. So my question is, check whether root 2 is an irrational number or not. So as I told you, we will be adopting the contradiction method. So let's assume that root 2 is rational. So obviously, if we assume that root 2 is rational, then we can write it in the form of p by q. So root 2 equals to p by q. Now we'll square both sides. We get 2 equals to p square by q square. We can write p square equals to 2q square. So p square equals to 2q square. What do we get from this particular expression statement? That p square equals to 2q square means 2 is a factor of p square and q square is also a factor of p square. Now one more concept, that is, if we write 4 square means 16, and that can be written as 2 into 8. So you see, if you look at 2 is a factor of 4 square, and you can also check that 2 is a factor of 4 also. So if any number is a factor of the square of any number, then that number is a factor of that number also. That means if 2 is a factor of 4 square, then 2 is a factor of 4 as well. Okay. So if 2 is a factor of p square, then 2 is a factor of p also. So therefore 2 is a factor of p. So if 2 is a factor of p, then we can write p as p equals to 2 into m. So if 2 is a factor of p, you can write p equals to 2 into m. So again we square both sides. 4m square. So if you name it as 1, so we'll substitute the value of p square in 1. So in place of p square, write 4m square. So 4m square equals to 2q square, or q square equals to 2m square. This is number 2. So what we find from here? We find that 2 is a factor of q square. So obviously 2 will be a factor of q also. So we write 2 is a factor of q. Now what we get finally? That 2 is a factor of p and 2 is a factor of q. That means p and q are not co-primes. Is it clear? So p and q are not co-primes. So for a number like p by q, so if root 2 has to be rational, then p and q should have been co-primes. So since 2 is a factor of both p and q, they are not co-primes. Hence, it is not rational. Hence, it is irrational. Okay? Is it clear? Okay. Hope you remember the bag of rational numbers. Now if we now put all the irrational numbers into the bag, will there be any number left on the number line? The answer is no. So it turns out that the collection of all rational numbers and irrational numbers together make up what is called the collection of real numbers and is denoted by capital R. Okay. So we denote real numbers by capital R. So we define real numbers as the numbers which are positive or negative, whole numbers or decimal numbers, and rational numbers or irrational numbers are called real numbers. Example we can take, the examples are 2 is a real number, 1 by 3, then minus 3, then root over 2, and so on. Okay, so now since we have studied about the rational numbers, we have studied about the irrational numbers, and we have now come to know about the real numbers, which is a combination or the collection of rational as well as irrational. Rational number we have defined as the number which can be expressed in the form of p by q, and where p and q are integers and q not equals to 0. Similarly, on the other hand, irrational numbers are those numbers which cannot be written in the form of p by q, where p and q are integers and q not equals to 0. Right. Now we are going to study rational and irrational numbers from a different point of view, that is by decimal expansions of real numbers, and we will see how can we use expansions to distinguish between rational numbers and irrational numbers. Now basically there are generally three types of decimal expansion. So generally there are three types of decimal expansions. Let us see what are those. The decimal expansions there are three types of decimal expansion. The first one is terminating decimal. Second one, non-terminating. But repeating. So we'll come to know one by one. And third is non-terminating and non-repeating. Okay, so these are the three types of decimal expansions. The first one is terminating decimal, second was non-terminating but repeating, third one is non-terminating and non-repeating. So let's start with the first one, that is terminating decimal. Now let us consider the number 1 by 4. So if we divide 1 by 4, we get this 2, 0, 4 into 5, 4 5s are 20. So this is 0. So what we see here is that the remainder is equals to 0 and decimal ends at 5. Therefore, this is a terminating decimal, or you can say the expansion is terminating. Okay, so you divide 1 by 4, so you take the number 1 by 4. So when you divide 1 by 4, we get the quotient at 0.25, remainder at 0. So what you can write, that remainder is 0 and the decimal ends at 5. So further we need not, or we are not supposed to go for the division process once again, because you already come to an end here. So this is a terminating decimal. So let's take another example. Suppose we take 3 by 8. So let's divide 3 by 8. 0.0. So 8 3s are 24. This is 6 0. 8 7s are 56. This is 4 0. And 8 5s are 40. So again here also you see that the remainder has come to 0. So here also we write the same thing, remainder 0, and the decimal ends at 5. So this number is also a terminating decimal. So what we can say is that a terminating decimal expansion means the decimal expansion terminates after a certain number of digits, or we can say it contains a finite number of digits after the decimal point. Okay, so now please have a look. So we have come to know about what is a terminating decimal. So we have performed the actual division to find whether the number is a terminating decimal or not. Now we will try to find whether a number is a terminating decimal or not without performing the actual division. So p by q, if we take the number p by q, this is terminating if number 1 or a, p and q are co-primes. That is, they do not have any common factor other than 1. And number b, q is of the form 2 power n 5 power m, where n and m are non-negative integers. Or whole numbers, you can say whole numbers. So in order to prove that a number is a terminating expansion, decimal expansion, without actually performing the division method, then we have to prove these two conditions, that p and q are co-primes, the two numbers have got no common factor other than 1, and the denominator q is of the form 2 power n 5 power m, where n and m are non-negative integers, or you can say they are whole numbers. Okay, now let's illustrate this with the help of an example. So let's take an example. So let's take the number 11 by 20. Okay, now here 11 and 20 have no common factors. So therefore 11 and 20 are co-primes. Now let us find the factors of 20. So if we find the factors of 20, prime factors, 2 tens are 20, 2 into 5, 5 into 1. So 20 can be written as 2 power 2 into 5 power 1. And here we see the denominator is equals to 2 power 2 into 5 power 1. So it is of the form 2 power n and 5 power m, where n equals to 2 and m equals to 1. Hence, it is a terminating decimal. So what we did here is the number is 11 by 20. So it is the numerator p is 11 and q is 20. So if you see carefully, you will find there is no factor common between 11 and 20 other than 1. So 11 and 20 have no common factors. So 11 and 20 are co-primes. Now let us find the factors of the denominator q, which is 20. We get 20 as 2 power 2 into 5. Now denominator is 2 power 2 into 5, so which is of the form 2 power n 5 power m. So where n is 2 and 5, m is equals to 1. Hence it is a terminating decimal. I think it is clear now. We take another example to make it more clear for you. Okay, let's take another example. So let's take this number 29 by 343. So 29 by 343, if you take this number, obviously we see that there is no factor common between 29 and 343 other than 1. So they are co-primes. So the first condition is satisfied. So here we can write 29 and 343 have no common factors. Therefore 29 and 343 are co-primes. Now let us factorize 343, the denominator. So 343 think it will go with 7. 5 so 37, 7 4 to 28, 6 7 9 64. So this is 7 7. That is 7. So we have 343 equals to 7 into 7 into 7. So denominator is 7 power 3, which is not of the form 2 power n and 5 power n. Hence, it is not a terminating decimal. But if it is not a terminating decimal, then what it is? It is something it is. So if it has to be terminating decimal, then its denominator, so p and q have to be co-primes, and the denominator should be of this form of 2 power n, 5 power n. M, where n and m are non-negative integers or whole numbers. Here you can see the denominator has got 7 as a factor. So it should not have any factor other than in terms of 2 and 5 in order to that it should be called as a terminating decimal. Now if it is not, since 7 is present as a factor of this particular number of this denominator 343, so this is not a terminating decimal. So we can call this as a non-terminating repeating decimal. So this is non-terminating repeating decimal. So we know very much that what is a non-terminating repeating decimal. Non-terminating means the division will never come to an end, and repeating digits after the decimal point. It may be 1 digit, it may be 2 digits, it may be more than 2 digits, will be repeated after some interval. Okay, so that is why it is called non-terminating repeating decimal. So please have a look. I hope you have understood this, and now I will give you some questions to solve and see that you get the answer, and just follow whatever has been told here, whatever has been discussed, exactly the same way you go ahead, and I think it will not be a problem for you to solve the questions right now. Okay. Question number 1. Without actual division, so that each of the following rational numbers is a terminating decimal. Express each in decimal form. (24 by 125). Next is 171 divided by 800. Then we have 15 divided by 1600. 17 by 320. 19 divided by 3125. So these are the 5 questions which you will be solving, and you need to prove that these are terminating decimals as in the question it is given actual without actual division, so that each of the following rational numbers is a terminating decimal. So the conditions remains the same. First is that P and Q are co-primes and Q is of the form 2 power n and 5 to power n, where n and m are non-negative integers or whole numbers, right? So you just try and express each in the decimal form. But since this is very simple, because when you are getting 125, let us take 125, if you factorize it, so 5 into 25, so it is 5 into 5 into 5, so it is 5 power 3, right? So it is 125. So multiply any number so that it becomes a number having like make the denominator as 0, means 100, 10 or 100 or 1000, something like that, and then taking the decimal. Very simple. Okay, so do this. Next question is question number 2. Without actual division, so that each of the following rational numbers is a non-terminating repeating decimal. Seven by 210, 32 by 147, 29 by 343. I think this particular one we have done already. 64 divided by 455 and 11 divided by 2 power 3 into 3. So solve the two questions, and the first question is to see that the numbers are terminating decimals, so without performing the actual division, and second one also they are non-terminating repeating decimals. Okay. Now look into this. This is non-terminating decimal. It is divided into two categories. One is the repeating decimal and there is the non-repeating decimal. If it is repeating decimal, that means it can be converted into a fraction, and if it can be converted into a fraction, that means in the form of P by Q, then it is rational. Okay, now come to this side. It is a non-repeating decimal, so it cannot be converted into fraction, and hence it is irrational. So this is, if you see into the non-terminating decimal expansion, so there are two types of non-terminating decimal expansions. Number one is the non-terminating repeating decimal, and there is the non-terminating non-repeating decimal. So the one which is non-terminating and repeating are rational numbers, and which are non-terminating and non-repeating are irrational numbers. Okay. The non-terminating but repeating decimal expansion means that although the decimal representation has an infinite number of digits, there is a repetitive pattern to it. Now, if you see non-terminating decimal, under which if you see to the repeating decimal, see for example 1 by 7 equals to 0.142857. So if you continue with this division, you will find after this again you will find 142857. If you further continue, then again you will get 142857. That means what? This sets of digits, this which is under this bar, keeps on repeating. So that means the pattern of digits keeps on repeating in the case of repeating decimal, right? So in non-terminating but repeating decimal expansion, the prime factorization of the denominator has factors other than 2 and 5, as we have already studied that is in terminating decimal the factors of the denominator are in terms of 2 and 5, but in a non-terminating but repeating decimal, the prime factorization of the denominator has factors other than 2 and 5. Now when you come to non-terminating, non-repeating decimal, so the non-terminating, non-repeating decimal expansion means that although the decimal representation has an infinite number of digits, there is no pattern to it. The ellipses, that means the 3 dots, tells us that the sequence of digit never ends. So what we see, that any rational number can have two types of decimal expansions. Rational number can have two types of decimal expansions. Number one is the terminating decimal, and number two non-terminating but repeating. And any irrational number can have only one type of decimal expansion, that is non-terminating, non-repeating decimal expansion. Okay, is it clear? Okay.